Yeah. Intangible mobile augmented reality for collaborative learning. So this presentation is about a preliminary study that focuses on user needs, experience, and interaction design of a tangible mobile AR educational game regarding the operation of the mobile device. We hope that this is the first step to our long-term goal towards specific factors and guidelines for designing collaborative tangible mobile AR games for young students. But first, let's talk a bit about teaching computational thinking, which is our learning objective in this context. There are three main techniques in teaching computational thinking: visual programming with block-based interactions and plug activities without the use of any technological mean, and physical programming that combines visual programming languages with physical elements or electronics like robotics. All these techniques are commonly combined with game-based learning, which provides a means to develop high-order skills like analyzing, synthesizing, and more due to the attributes of that the game have already built in. There are many ways to use games for teaching computational thinking. For example, you can use it as a teaching technique through gameplay, or a teaching technique like through game design, or even as examples in teaching computer science concepts like computational, like sequence, algorithms, loops, and more. The last technique we mentioned, which combine physical and digital, can be well served with mobile AR, which is our focus today. So tangible mobile AR is quite different from traditional interfaces, as it provides spatial interaction, real-world and physical interaction, and also visual overlays in the user's field of view, compared to traditional interfaces, which is mostly screen-based. That creates new challenges, especially regarding technology feasibility, content manipulation, and device operation. About collaboration in tangible mobile AR, studies shows that flexibility, that it can offer flexibility in manipulating virtual objects within a shared physical space. It supports natural coordination behavior and non-verbal cues among participants, and with tangibility, it facilitates coordination and supports faster and more natural interactions. But on the other hand, evidence shows that some members may be excluded from collaborative engagement. That may be due to design issues. And finally, current research focuses more on remote AR collaboration and the manipulation of virtual objects. For example, some studies explore the manipulation of virtual objects through a second mobile phone, or the combination of 2D gestures with a mobile phone orientation, or even kinesthetic gestures with lip motion. But what about the physical part of that equation? So about manipulation and usability in tangible mobile AR, research suggests a lot of factors that are really important and needs to be addressed. Some of the most important ones are the co-manipulation of both physical and digital objects, the multiple factors that contribute to different types of tracking loss, which may be confusing and time-consuming for the users, the screen size and the number of devices, the device operation, as we stated before, whether the students or the users use two or one hand to handle the device, and the field of view that users have of both physical and virtual world. So there's a lack of definitive interaction designs at this specific design application, especially for young students collaboration. And that's where our research come in. Our research questions focus on how the placement of the device can affect the collaboration of the students, especially regarding the field of view and the opportunity for the students to use both hands while manipulating the device and the physical manipulatives. Two important factors we measure are the ease of use and the active participation of all users. Also, we wanted to see if there is evidence that enjoyment and engagement differentiate between the two settings. So the prototype we use for this experiment is AR Quest. It is a collaborative mobile game for developing computational thinking skills for primary school students. The storyline follows a pirate that is in a treasure hunt. Of course, it is mobile AR game with tangible manipulatives. It uses game-based learning approach in a collaborative context. It uses low-cost and widely available equipment as we talk about mobile devices and paper markers. And while our game follows the general approach that most of the research in this field use, we have both attributes of teaching through game design and through gameplay. The goals for the game is to be entertaining, to afford the collaboration, and to support the development of computational thinking skills. So how does it work? There are two teams, the designers and the solvers. The designers play first. They have to create a challenge by placing physical tokens on the physical board, and then by scanning their challenge, they send it to the solvers, where they have to create a solution for that challenge by using the command tokens, and then run and see the results. Okay, let's see a short demonstration about the gameplay. Okay, so the study we conducted took place within 2 sessions within subject design in non-typical education settings. And we wanted to compare the 2 different settings that you can see on the images. And the first, the stand-mounted device, where the mobile device is fixed on a mobile stand. So that means that the players, the students, have the opportunity to use both hands for manipulating both the physical and the virtual elements of the game. And the field of view is stable and predefined. On the other hand, we have the second condition, where the handheld setting, where the mobile devices is held by one of the team members. The participants of our study were 8 students, 8 to 10 years old, 4 girls and 4 boys. And the factors we measure was the user perception of technology ease of use, the active participation of all participants, and the perceived enjoyment. We used the observation of participants' interaction, the think aloud method, and screen recordings. Screen recordings were later analyzed in order to give us some data regarding the if the students achieve their goal, and also the number and categories of different tracking losses, which will give us later more insights and support our findings. Regarding the limitation of the study, unfortunately, at the second session, instead of 4 games, only 3 took place due to time restrictions. Although all students tried out both settings, either as designers or as solvers, the sample was quite small, and the study was partially relied on self-reported data. About the results, regarding enjoyment and engagement, there was no significant difference between the 2 settings, although our observations were quite positive, as many children ask us where they can find the game or buy to play again. And at the end of each session, during the discussion with participants, 6 out of 8 students stated that preferred the stand mountain settings because it was less tiring. In terms of performance, most groups achieved their goals. And during the stand mountain setting, the average time was shorter, which is an evidence that that setting may offer better ease of use. Regarding ease of use, the students during the handheld setting, the students held the device with both hands, so there was no free hands in order to use for the interactions with the tangible elements. Also, the field of view was limited, especially for some students, as the one student was holding the device and the other was mainly manipulate the tangible elements, and the student that was holding the device was the one guiding them. So there was also more issues of losing focus during the scanning of the markers, as the students aim too close or too far. And on the other hand, during stand mountain setting, there was more interaction with the tangible element, as the students have both hands free to interact with them. They shared the field of view, as they can both stand in front of the mobile device fixed on the stand. The device was stable, so we had less issues with scanning the markers. But in both settings, we observed the difficulty in scanning many markers at the same time. Regarding active participation of all users, during the handheld setting, we observed a turn-based game where the students, as I said previously, the one student was holding the device and the other was manipulating the tangible objects with their guidance. So there was no team decision making. The one that had the good field of view, that was seeing also the virtual and physical world. That was the one that took the decision, and the other were following their instruction. On the other hand, stand mountain setting, students work in the same task at the same time together, and more interesting conversation regarding the game where took place. Regarding the conclusions, our early results favor the stand mountain device, but we need further research to have conclusive findings. And some advantage for the mobile stand are that it can accommodate different heights and perspective, improves the communication and natural interaction between the students, and there's an opportunity to use both hands for multitasking. And the field of view, as there are evidence that the field of view can impact team communication and collaboration, as we see that larger field of view can enhance the sense of shared presence and teamwork. About the future, we need to address some image recognition issues. We want to expand the study with more players and explore group formation and dynamics as a substantial contributor to quality of collaboration, and address more ergonomic and usability issues to enhance collaborative engagement and the learning process. Thank you.
Thank you, Anna. Any questions? Yes.
Yes, thank you. Very nice talk, and I can see a lot of work behind the scenes on this. Maybe my question is a classic augmented reality question. So you use tangible interaction. What's the benefit of using tangible interaction in this context? The tangible augmented reality in the context of your work, because you could also do it just on a screen without the tangible interaction with the cards. So what's the benefit of the tangible side of things?
As I said before, if I find it, there's evidence that tangibility and interactions and manipulation in the physical world help students in order to coordinate their actions with the teammates and to better understand each other. Like they can show that this can take this may be here or no. They have more interesting discussions over that, and also it can help with motor skills and not in the collaboration part. Thank you.
Right. Okay. Thank you.
Okay. One more question.
Yeah, thank you for the talk. I also like the bottom line with the advancement. It's a very good visual and less cognitively demanding than having numbers. So it's a good example. I liked it. Just a question relating on the setup. Now, when we do an experimental design and we try to compare two cases or situations as an independent variable, you expect to find some interesting results. Now, once you set up your experiment, I knew the result. I knew that one was all red and the other is going to be all green, because obvious. Instead of having to hold a mobile device and through the mobile device to try to, on the other hand, try to manipulate the physical objects, that's tiring. It's obvious. It's nice to have this setup where this is, I have both my hands free and stable. It creates a single field of view condition. So it's obvious that the answer of this setup will be in favor of the second condition. I mean, what's the motivation of checking these two? I would more be interested with the previous question. Like, we know we have tabletops, like now with the various devices like tablets, etc. So this kind of setup, I would like to compare it, and also in terms of computational thinking, which is the main objective. How favorable is this setup, one of the two you use, against a more traditional tabletop where you can manipulate objects on the surface, which by the way will be much bigger, and you have other affordances. So this is my first question. And the second, but I don't know, probably it's me not following very carefully. I couldn't understand clearly the mechanics. I mean, what was the? I realized you had some kind of visual command language with arrows and go right, go left, to etc. Okay, but what did the other guys do? The designers? I mean, what were the clues, the hints for this? I just missed that. So
Okay.
May I suggest that the second question be answered afterwards, because I suspect that there's a lot to it. And the first question about.
Yeah, about the first question, I don't completely agree with that it was obvious, because we are talking about young students, and it may be obvious for adults, but young students, I don't think it's the same, because when the device is fixed, it may not give them the opportunity to work as they want. Like, sometimes at some point, maybe they need to take the device and put it aside and only focus on the tangible manipulatives, and then bring it in front of them again. But with the fixed base, that's not possible. It's a factor that I wanted to explore. Yeah, but also this is a preliminary study in order to use in my next study, where I want to compare the one with a base with more devices, like more screen, a bigger screen, like tablet. It's a first step.
May I just add also, it would be interesting to look at the difference between the roles. So the designer role and the player role, because I suspect that the designer role, for example, the hypothesis could be that may need a static, a mounted, much more than the player, which has a different type of dynamic. So the static may not be the solution for that. So a lot to consider for further studies. Thank you.
Thank you.